Hey guys, so we're doing the second part of section 4. So still doing like limits at infinity. So now they specifically talk about it in terms of sequences. So if you remember what a sequence is, so it's basically a, this is going to be like the worst definition ever. I'm going to say a sequence of numbers that follow a specific pattern. So if you remember when we did sequences, when we wrote sequences, we had like a sub n, and n was the first term. Yikes, that is supposed to have an s, first term. Okay, so a sub n could be anything. It could be like 1, 2, 3, 4, 5. That's a sequence because my pattern, I'm adding 1 every single time. My first term is 1. So those aren't very like creative. And if I was finding like the limit of that sequence, you can tell as I'm approaching infinity, I'm just going to be increasing with a bound, so this limit doesn't exist. So I specifically still want to be working with limits that are still like converging basically, so they're approaching that horizontal asymptote. Sorry. Okay. Yeah, so we still wanted to work with rational functions. Okay, so we still are going to find the limit as x approaches infinity of a sub n, and it's still going to be whatever the limit's going to be. So basically, a sub n is acting as like f of x right now, so a function. We have two words, and I already used one, so we had converge. So this means that a limit approaches a number at infinity. So basically they're converging to a specific number. So when you hear the word converge, you should hear like everybody's like going to this one specific spot we're converging. Okay, so the same thing with limits. We are approaching one specific number. We're trying to find this one location at infinity. We also have like the antonym of this. Did you hear that English word? Sorry, I'm really impressed with myself. Woo, antonym. Okay, so diverge means a limit doesn't approach a number at infinity. So remember, when limits don't exist, it could be, like with my example up here, it could be going into infinity. So I don't have a limit because it's not approaching a specific number. We could have a limit doesn't exist when it's like oscillating between two numbers, so it's going up and down between like -2 and +2. A limit doesn't exist when it's approaching two different values from the left and right, so diverging, basically a limit doesn't exist when it fails those three cases. But we're still going to use what we did yesterday to find limits of sequences. So this sequence, a sub n, is 4n plus 5 divided by n minus 1. And I could find like the first few terms of the sequence if I wanted to, but I can use the rules of rational functions from yesterday. So yesterday we learned I can evaluate based on the degree of my numerator and denominator. So the degree of the numerator is 1, same thing with the denominator is 1. So we have like n equals m. So it's like the second case or something. So the limit as I'm going to say n approaches infinity, since that's our variable of a sub n, is 4 over 1, or 4. So remember, we take the leading coefficient of the numerator, the leading coefficient of the denominator, write it as a rational number, and then simplify, just because the degrees were exactly the same. So if they weren't, then there's different cases. Here is a different example. So a sub n equals 4n plus 5. Over n squared minus 1. So same thing, I'm comparing the degree. Oops, I don't want that color. The degree in the numerator is 1. The degree in the denominator is 2. So 1 is less than 2. So when it's less than, we should know the limit as n approaches infinity of this function. Since it's less than, that means my horizontal asymptote basically is the x-axis, so it's approaching 0. Remember, if it was greater than, then it's approaching, or it doesn't, the limit doesn't exist, sorry. If it's equal to, then it's the leading coefficients. If it's less than, it's 0, greater than, doesn't exist. Okay, here is a complicated one. So we have 5 over n to the third is the first part. And then I have times n plus 1, 2n plus 1, all over 6. Okay, so, I mean, it looks complicated, but it's still not that bad. I want to find the limit as n approaches infinity of a sub n. So let's just take this a piece at a time. So I need to first evaluate the degree of the numerator and the degree of the denominator. So if I'm looking at this, the denominator is the easiest. The degree is 3, clearly. But my numerator, it doesn't really specifically say because I have this product in my second fraction. But if I was actually like going to distribute this polynomial up here to figure out what the degree is, I would distribute n to 2n, and I would get out 2n squared. And then I'd have plus whatever. I honestly don't care about the rest of it. And then I still have this n in front. And then I distribute the n to 2n squared, and I'd have 2n to the third. So the degree in the numerator is to the third power. So I have equal degrees. So that means I need to figure out what is the leading coefficient of the numerator and the leading coefficient of the denominator. So I can work all of this out. So if I take what I already started, I'm going to start here with the 2n squared plus my nonsense. So basically why I don't care about the nonsense is because I just need this leading coefficient. I don't need to worry about like the rest of it because it's basically a waste of time. I could find it if I want to, but it's really not necessary. My denominator, if I write these two together, is 6n to the third power. Okay, so if I just write 5 times n as 5n instead, so it doesn't look so weird, I'm distributing 5n to 2n to the second power, and I have 10n to the third over 6n to the third. And sorry, this should still, like, this should be the limit as n approaches infinity of this. Yeah, so I should have limit as n approaches infinity. Sorry, my notes are like all out of whack. So then I have an equal sign. Okay, so since my degrees are the same, and numerator I have plus whatever all this other stuff is. I just want to worry about the leading coefficient since the degrees are the same. Clearly you can see that. So I just need 10 over 6, and this simplifies by 5/3. So that's the limit of this sequence. So that was, I could have explained that a lot better, but I was, bleh. Anyways, here is our last example, our story problem. Okay, so it's not that bad. We're still doing limits, so it's nothing new. It says you're manufacturing greeting cards that cost 65 cents per card to produce. Your initial investment is $4,500, which implies that the total cost C of producing X cards is given by this function. So the average cost C prime per card is given by C prime of X equals C over X, which is that. Find the average cost per card when X is 5,000, 50,000, 500,000, and the limit of C prime as X approaches infinity. So if you remember C prime, that's like the derivative. So it's really kind of weird. Actually, I don't think C prime is acting as the derivative. I don't know why they put that notation there. They should make that different, I want to say. I don't know. Basically what we need to do, so if we're finding average cost per card, average cost is given by C prime. So we're using this fraction right here. So if you want to rewrite it, C prime of X is 0.65X plus 4,500 all over X. So if I want to plug in 5,000, I absolutely can. So that's what you're doing for the first 3. So 0.65 times 5,000 plus 4,500 divided by 5,000. So let me type that in really quick. The numerator is 76 7,750. I'm dividing by 5,000. I get my average cost per card of $1.55. So let me do the next two. So plugging in 50,000. So numerator, I get 37,000. I'm dividing by 50,000. And I get my average cost per card to be 0.74. And last but not least, plugging in 500,000. And the numerator, I get 329,500. And I'm dividing by 500,000. And I get 0.66 if I round. Okay, so you can see these are like, they're converging to a specific number. So they're decreasing, but they're not decreasing like at an even rate. They're like, we're decreased by like 0.75. And this was like 0.1. So we're slowing down our decrease rate, if that makes sense. So we're converging. So then I could find the limit as x approaches infinity of c prime of x. So this is the same thing. So we're looking at this guy, comparing the degrees since it's a rational function. The degrees are the same, they're to the first power. So when the degrees are the same, I want to look at the leading coefficients. So my leading coefficient in the numerator is 0.65. Leading coefficient in the denominator is 1. So my average cost is approaching 65 cents. So that's technically my horizontal asymptote. So they're saying the more cards that you produce, the average cost to make them is getting cheaper. It's approaching 65 cents. So that is it for sequences and limits of rational functions. That's your homework assignment. You have a quiz tomorrow over section 4. Like always, let me know if you have any questions over this assignment.